You've probably heard the term regression analysis thrown around, right? But what does it actually do? Well, let's forget all the complicated stats for a minute. Just think of it as a kind of crystal ball for data, a tool that finds hidden patterns in chaos so we can get a glimpse of the future. Let's dive in and see how it works. Okay, think about this. A company drops millions on a huge new ad campaign, but how do they really know if it's working? For every single dollar they spend, how much does that actually boost their sales? Or, hey, what about something closer to home, like buying a house? You see that price tag, but is it fair? How much is that great location really worth compared to, say, the square footage or the number of bedrooms? And if we zoom out to a massive scale, how do power companies figure out how much electricity to generate for tomorrow? I mean, it depends on the weather, the day of the week, a million different things. How in the world do they get that right? Well, the answer to all of those questions, from ads to houses to the power grid, it all comes down to one thing: finding the hidden pattern in the data. And that is exactly what regression analysis was built for. It's the go-to method for solving these kinds of puzzles. Let's circle back to those house prices. Imagine you took the data from 100 different houses and just plotted it on a graph. You put the size along the bottom and the price going up the side. What you'd get is this big cloud of dots, right? But you'd notice, as houses get bigger, they generally cost more. The cloud would kind of drift upwards and to the right. There's a real relationship there, a trend that's just hiding in all that noise. Now, here's what regression does. It looks at that cloud of dots, and it finds the one single, perfect, straight line that slices right through the center of it all. And this isn't just any old line. It's what we call the line of best fit. It basically represents the core relationship between size and price, clearing away all the random stuff. And that, right there, brings us to the official definition. Regression analysis is just a statistical tool for modeling that exact relationship. The thing we want to predict, like the house price, we call that our target variable. And the clues we use to predict it, like the size of the house, those are our predictor variables. Simple as that. So let's start with the most basic version of this. To keep things really clear, we're going to begin by using just one predictor variable to try and guess our target. This is called simple linear regression. Okay, now this might look a little like a formula from high school math class, but trust me, it's incredibly powerful. This little equation is the recipe for that straight line we were just talking about. So y is the price we're trying to predict, and x is our one and only clue, in this case, the size of the house. But the real magic, the secret sauce in this recipe, is that b1 right there. That's the slope of our line. It tells us exactly how much the price, y, is expected to change for every 1 unit increase in our clue, x. So if B1 turns out to be 200, it literally means that for every extra square foot of space, the model predicts the price will go up by about $200. It puts a hard number on that relationship. But of course, the real world is almost never that simple, is it? One clue is a great place to start, but you know what? More clues are almost always better. And this is where things get a lot more sophisticated and way more powerful. I mean, a house's price isn't just about its size, right? Think about it. A tiny apartment in a perfect downtown location could easily be worth more than a huge house out in the suburbs. The number of bedrooms, the age of the house, these are all super important clues that we were leaving on the table. And that brings us to multiple linear regression. All we're doing is expanding our little formula to include all those new clues. We still have our target, y, the price. But now we have multiple predictors, x1, x2, and so on, for size, location, age, whatever. Each one gets its own special slope, its own b-value that measures its unique impact on the final price. This lets us build a much, much richer and more accurate model. All right, so we've built a model. It draws a line, it makes a prediction. But this brings us to probably the most important question of all. Is it any good? How do we actually know if we can trust its predictions? So we've got our line of best fit, but how best is it really? I mean, do the actual data points cluster up really tightly around our line? If so, that's great. Our predictions are pretty close. Or are they just scattered all over the place, meaning our model isn't really helping us much at all? To answer that, we use a simple score called R-Squared. The easiest way to think about it is like a report card for your model. It's a grade on a scale from 0 to 1. It tells you what percentage of the changes in your target variable, like why some houses are expensive and others are cheap, can actually be explained by the clues you gave the model. An R-squared of 1.0, That is the holy grail. It means your model is 100% confident. All the real-world data points fall perfectly on your prediction line. Now, this almost never happens in the messy real world, but hey, it's the goal we're shooting for.
A more realistic score for a pretty good model might be something like zero point 0.7. This means that our clues, size, location, and so on can explain about 70% of why different houses have different prices. That's actually a really solid model with some serious predictive power.
And then, on the other end of the spectrum, if you get an R-squared of, say, 0.1, well, that's not great. It means your clues only explain about 10% of what's going on. The relationship is just way too weak, and your model's predictions are basically just random guesses. So now we know what regression is, how it works, and how to tell if it's any good. So let's zoom out and take a look at where this incredible tool is actually being used and what its real-world impact really is. Now, like any tool, regression has its strengths and its weaknesses. The awesome thing about it is that it's simple, it's fast, and the results are pretty easy for us humans to understand. But it does have an Achilles heel. It assumes the relationship is a straight line. If the real pattern is a curve, linear regression will miss it completely. It's also really sensitive to outliers. A few crazy data points can literally pull the whole line off course and totally wreck your predictions. And this shows you how it's done in the real world. See, it's not magic. It's a clear, repeatable playbook. You start by identifying the problem, you collect and clean your data, then, a really key step, you split that data. You use most of it to train the model, but you keep a little chunk aside to test it later on something it's never seen. After you build and train it, you evaluate it with that R-squared score, and only then, if it's good enough, do you actually deploy it to make real predictions. And believe me, this playbook is being run absolutely everywhere. Think about it. Wall Street uses it to model stock movements. Businesses use it to forecast next quarter's sales. Marketing teams use it to prove their ads are actually working. Hospitals even use it to predict patient needs and costs. Regression is the quiet, powerful engine driving decisions in pretty much every industry you can think of. So, at the end of the day, regression isn't some scary black box. It's a logical, powerful, and honestly, a pretty intuitive way to find the signal in the noise. It helps us understand the hidden relationships that shape our world. So now that you know the basic recipe for prediction, what pattern would you want to uncover? What would you predict?